big deal. Whoa, he goes cray, cray, cray. It's Friday. Regardless, you will have time to work on your immunity project today. On Monday, the entire 2 periods, and then on Tuesday, you'll have probably half the time. On Tuesday, the project's going to be due on Wednesday. I'm going to start notes for the next unit on Tuesday, which will be cell cycle. It won't be that long of a unit. I want to get started on it early because the sooner we get through that one, the sooner we can start reviewing for your cumulative that's going to be before break. So I want to get through that and make sure you have time to work on that as well. Questions on anything? All right. Yesterday, we left off with talking about antibodies. And just to kind of refresh your memory and do it again, because I feel like the more times it gets into your head that you hear it, the better it's going to be in your brain. The more solid those connections will be in your brain, and the more likely you're going to remember it. So yesterday we were talking about B cells. Now B cells are they're first initiated because of what cell? What is the cell that's going to say there's a problem here, guys? There's a problem. T cells. We have these helper T cells. Good. And these helper T cells, they actually are told that there's a problem from our little puppy that has a little antigen saying, look what I just ate, right? He's displaying that antigen on the surface of the cell membrane. That's the macrophage.
Wait, is it displaying the antigen or the pathogen?
It's displaying the antigen, which is part of the pathogen. Yeah. So it's just a part, and what part it displays could be different, but the first one to get that message to the T cell kind of determines which part of the pathogen it will then go after. And so then once that happens, those B cells are going to sound the alarm, or they're going to not sound the alarm, the T cells sound the alarm. And then that's going to cause a bunch of B cells to be made. Where's my B cell picture here? I wanted this one. And my B cells will form antibodies, which are just proteins. The B cells themselves will display the antibodies on their surface of their cell membranes, as well as they will also eject them into the body, and then they'll float around in the bloodstream and the lymphatic tissue looking for anything that they match to. Now, the antibodies can have different shapes depending on what the T helper cell originally picked up from the macrophage. So the shapes could be different. And that's why these different vaccines that we have for COVID, they are looking for the same pathogen, but they're not necessarily looking for the same part of the pathogen. And so over time, as the virus changes, as it mutates, that piece that it's looking for might no longer be produced by that pathogen from generation to generation. And if that happens, then it would be less likely to be tagged by an antibody because now the antibodies really aren't effective. Tyler, do you have a question?
No, I was stretching. Sorry.
Oh, okay. No worries. So we also make these memory cells, and those memory cells are going to stay out in the bloodstream. They'll stay out in the lymphatic tissue, and they're going to be there in case another infection comes along. So you get over your sickness, but maybe the rest of the school is sick. You come back, and you're not going to get it because now you have these antibodies. And so even though you are actually getting it, but your body is fighting it off before you become symptomatic and getting rid of it very, very quickly. Okay, so that's how B cells work and antibodies work, but we still haven't actually destroyed anything. So now we need to look at the other part of that adaptive immunity, which is the cell-mediated immunity. So we're going to look at now what actually the kind of foot soldiers, so to speak, the ones that are going to go in and they're going to destroy any cell that has been tagged or marked by the antibodies. So T helper cells activate not only B cells, but they're going to activate these things called cytotoxic T cells. Cytotoxic T cells are going to look for any antigen-presenting cells. So they're also going to look for macrophages. They're going to look for macrophages that are, hey, look at me, I've got this really cool toy. And well, they're actually going to get destroyed by those cytotoxic T cells. And then the cytotoxic will also look for any cells that are marked for destruction by the antibodies. So cytotoxic T cells recognize the antibodies attached to either an infected cell or the pathogen itself. So there may be viral particles floating around in a pathogen floating around in the bloodstream that hasn't attached to anything yet. And the cytotoxic cells, because there's an antibody attached to it, it's going to get rid of it. How does it do that? It either tells the cell to start something called apoptosis. We haven't talked about that yet, have we?
No.
So apoptosis is programmed cell death. It's basically telling the cell, you need to kill yourself right now. Sorry. Because in some cases, the cell is just, it's infected. It's beyond repair, and it needs to be eliminated. If it's not eliminated, that infection will continue to spread. The other thing that it can do is, and there's pictures shown on the next page, is the cytotoxic T cell itself can initiate that destruction of the cell by forming these little pores in the cell that's infected. So here I have a cytotoxic T cell that is attaching to an infected cell here. And after it attaches, it forms little pores, creates little holes in the cell, and then water rushes into the cell, and that causes it to explode.
Wait.
Water rushes into the cell, makes it explode.
Yep. So it can either, like I said, it can either cause the cell to perform its own programmed cell death, or it will poke a hole in there. Cytotoxic T cells aren't all the T cells we have, though. We also have, in addition to T helper cells, we have memory T helper cells. And so they're just like the helper cells, only they're not going out and sounding an alarm, but they're going to be held back in reserve, also floating through bloodstream and lymphatic tissue, so that if there is another infection down the road, they will very quickly be able to produce cytotoxic T cells and say, hey, this is what the infection looks like, go, 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 and sound the alert to make everything start up again, B cells and all that start. Okay. Questions on that? Immunological memory is the ability of the body to remember the infections that you've had over time. The first time you get sick, that you're exposed to a pathogen, it takes a while for your immune system to do all this. For the T helper cells to get activated, for the antibodies to be produced and mark the cells, and then the T cells, the cytotoxic ones, to go in and clean up. So it takes a while. The second time around, you're much better, because now you've got the memory B cells. So you've got memory cells that can produce antibodies, and you've got the T helper cells that can produce, they can say, hey, go B cells, go do this. And they can also say to the cytotoxic T cells, go in and clean up the mess. So if you look at this graphic here, there's a couple of things to notice on this one. There's a line here in blue. First, and it says antibodies to A, and primary response and secondary response. So in the first example, it takes quite a while to get a lot of antibodies. Here they're saying that, I don't know if this is hours, or this is where it's important that you label your axes. I don't know if that's hours or if that's days. It must be hours, right? Hours? Days. It couldn't be days. Yeah, it has to be hours. So in the first response to that particular infection, it takes about 14 hours to get a decent response. But the second time that you're exposed, it happens. So between 28 and 35, you get a very large response very quickly. Much greater response, much more quickly. The first exposure, it actually took 7 hours before you even got anything. Here they're saying by the time you have 7 hours, you have 10,000 antibodies. Okay. But if now you're exposed to a second different infection, you go back to that. It takes, again, 7 hours to get to that. And because this is acquired immunity, every pathogen is going to produce its own unique response to that pathogen. Okay, so, my example would be, how was it last year? God, it was just last year. Last year I got strep throat, and then I didn't take care of myself, and I got on an antibiotic for strep throat. But then I did this crazy race that I was on my bike for 21 or 22 hours.
But you did that with the strep throat?
Yeah.
That's interesting.
I've been training for a long time for it. It was
You
dumb.
gotta do it.
I had to do it. I didn't finish. But anyway, what did I get the next week? Bronchitis. Yeah. Because now I had exposed myself to one virus. Wait. Strep is bacterial, actually. Sorry. One bacterial infection. And then because I had not let myself rest, now I'm producing antibodies to the strep throat, but I'm not producing any antibodies to other things because it's a specific acquired response. So my body didn't have anything for the bronchitis. So it had to go back to square one and build up immunity to the bronchitis, which took a while to get over. And then, of course, I got strep throat again because I didn't take care of myself enough. So it was just a hot mess. Maren. So antibiotics, all they are doing is they're not working on the antibodies. They are working on the infection itself. And typically antibiotics work through inhibiting protein synthesis by the ribosomes of the thing that's infecting you. So it's keeping that from going forward and making more of itself. And then that allows the immune system to kind of clean up. Right? If more is not being produced, then you can just kind of clean up and get rid of it. So this brings up immunization. So the reason we get vaccines is because we prime our immune system with that shot the first time. So that now what happens is we take a part of a pathogen. So we take an antigen off of the pathogen, just a little piece of it that is inert. In other words, it's not going to make us sick. However, it is going to generate an immune response. Okay? So sometimes after you get a shot, how do you feel? Bad how? Sick, right? You feel sick. You think, I just got an injection of a vaccine of COVID and now I'm sick. It made me sick. It's not making you sick. It's making your body think you're infected. And then it's displaying all those symptoms. It's displaying the fever, the aching, the lethargy, feeling really wiped out. But it usually lasts. Does it last for 10 days? No. Hopefully it only lasts for a little bit. I mean, I've heard cases where you've had no reaction. I've heard cases where it's a few hours. I've heard cases where it's a couple of days. But it's basically the reason you feel bad is because it's your body's immune system doing all these things to try and get rid of what's inside of you. Okay. So it's forming those antibodies and forming those memory cells, the T and the B memory cells for next time. Yeah.
Why does that only happen with some vaccines? Like flu, most people don't.
To be honest, I'm not sure why. I'm not sure why it is. Yeah, because I know I'm supposed to be getting a shot. I need to schedule a shot for shingles. Y'all know what shingles is? It's basically chicken pox on the inside. It's really not good. And when you get to be my age, you're supposed to have 2 shots, but each one of them like knocks you out pretty bad. So that's why I haven't wanted to take them. Yeah, Sophia.
So, like, is the difference in like the so you know how you're talking about the B cells having different shapes for the pathogen?
Yeah.
Is that why like sometimes the body when you get like your COVID vaccine is that why like you get different reactions? Yeah.
I think so. Yeah.
Because I had like I didn't have any reaction to the first one, and the second one just like out down.
Yeah.
The second one I was down. I was down out for like 4 days.
What kills me is, you know, you get your vaccine and you get a fever and you're like, this is so weird because I feel like I'm sick, but I know I'm not sick. You know, it's cool. I think it's cool that your body reacts like that. Oh man.
That is actually kind of sick.
All right, so the new vaccines. COVID was one of our first, or if not, it might have been the first mRNA vaccines. Now we haven't started talking about gene expression yet, but basically DNA is stored in the nucleus, and it never leaves. An mRNA, its job is to make a copy of DNA and to take it to the ribosomes, where you will make a protein. Okay, ribosomes make proteins. Well, what the new COVID vaccines are is it's actually not an antigen or pathogen, but it is the mRNA code for that antigen. And so our body makes a viral antigen, produces it. And then once it's produced, the body's like, wait a minute, this isn't supposed to be here. And then it forms a immunity to that, or it does the whole immune system. Okay, and specifically what it's been targeting are those spikes that we've been talking about. Targets the spikes on the COVID-19 membrane. Now, I don't know exactly why. I don't know the details of this, but I do know that the mRNA vaccines tend to work more quickly, and they tend to have less side effects than other non-mRNA vaccines. What's just really cool, I think, is the fact that they were able to. It just shows you how, you know, when we really have to, we can be on the same page. We can actually get something to happen. Because, you know, I don't think anyone before COVID would have said mRNA vaccines were anywhere close to being developed. And then all of a sudden, everyone's working on it. And next thing you know, we have like 2 companies who've come up with them. Herd immunity. So you heard a lot about this during COVID, about herd immunity and how everyone needed to get a vaccine. And why is that? Why can't, you know, if I'm immune, I'm fine. And you are fine. But the problem is the people who don't get it tend to pass it on to other people, and it just keeps going. So if enough people of a herd are immune, it will keep the pathogen from spreading throughout the population. Fewer and fewer people get the pathogen, and eventually it will die out. So what I wanted to show you was, this is from, I think, NPR. And I thought this was kind of cool. So this looks at just a simulation of, so all of the infected, well, starting off, everyone is healthy here. I think the dark ones here represent the people who are vaccinated. Oh. So these guys are vaccinated. And here it's 5%, here it's 30%, and here it's 75%. And then you can also look at the people who are infected. Let's make them pink. Hey, we got some here. We got some here. Got some here. So this is kind of a simulation to show what happens if, you know, a certain percentage of the population is vaccinated. Ready? Ready? Wait, got to go back. All right, here we go. Here we go. Oh, sad face.
The
Community one is like screwed, right? Yeah. So what happens is if everyone around you is vaccinated, then you're not going to be able to spread it to these other guys who didn't get the vaccine. Okay, but you have to have a certain percentage of the herd, the population, inoculated, or that won't work. Miriam.
It's like what we were actually just yeah.
It's just like idea that like
Yeah. So I haven't gotten COVID yet.
Really?
So,
Ever?
No,
we have just or like
we could have got it
I'm knocking on wood there. But what I have heard is that I probably have gotten it, but that my immune system like jettisons it out so quickly that I don't show symptoms and I don't test positive for it. So to answer your question, I don't know, but it could be that some people's DNA, maybe just for this particular, because it's not like I'm a superstar when it comes to immunity, but maybe in this particular case for this particular virus. And the other thing is, there was also at one point, there was a hypothesis that some people had been exposed to something like this in the past, which gave them some immunity. So if you were, I can't remember what, I feel like it was one strain of a virus, but I don't remember which. Yeah, it's a coronavirus, right. So, but I feel like there was one form of it, but I don't remember what it was. But maybe I was exposed to it and other people weren't.
I feel like that's probably true because I had this like weird rare thing when I was a kid, and like I never got COVID, and I really want to look up like what it looked like now,
Yeah.
because it might have like the same similar spikes close enough to the way that
Right. Yeah, for sure. Agreed. Agreed. Anyway, so that's herd immunity. This is just a graphic showing how vaccines can help against life-threatening illnesses. Here's our figure again now, showing how everything works. We've got our antigen presenting cell. I think this makes a little more sense now. Our macrophage cell, it presents, and that's going to activate these helper T cells. And the helper T cells are then going to activate the B cells and the cytotoxic cells. Helper T cells will also activate memory cells, T cells. B cells will go on to produce plasma cells as well as memory cells. Cytotoxic T cells produce memory cells, and they also produce active ones.
There's memory B cells.
Mm-hmm.
Is that just like ones that like?
Those are ones that can produce the antibodies really quickly because they already know what the shape of the antigen is. Anyway, that's a good one for you when you're looking at your project. Active and passive immunity. Active is something that you develop over the course of your lifetime. Passive is the stuff that you get from mom. So, for example, they often talk about how it's better to use breast milk if you can, because it has certain antibodies in it that you're not going to get from formula. I mean, obviously, that's not always possible, but if you can. Yeah. Tell me.
I don't know if this is true, but I feel like I heard like the way you were like birthed has kind of an effect on like your immune system, like a C-section compared to like a natural birth.
I hadn't heard that before.
I just like.
Does your immune system become more activated when you get a C-section?
I think it was like less because there's like less.
Oh. Less work for the baby.
Or like
less traumatic.
Yeah, that makes sense.
Yeah, I don't know. I hadn't heard that before.
I just wanted to see if that was like true.
I don't know. I can't say yes or no. I haven't heard it. Yeah. Immune rejection can happen. There are cells that are unique to you called MHCs. MHC stands for major histocompatibility complex receptors. Yeah, I know it's big. MHCs. These guys are on all of our cells, and they're unique to us. So the shape of these are unique to us. And this makes it complicated for when you want to transplant an organ, because there can be rejection if those MHCs are not close enough. And sometimes you can get away with, if you are siblings, for example, or a parent, there's going to be less rejection. But oftentimes, a recipient has to take anti-rejection medication so that the body doesn't reject the, heart or whatever it happens to be. Right, which compromises the immune system, which leads to other issues. Yeah.
Wait.
Yeah.
So, what happens with MHCs? Like,
So if I give you my heart, sad face, you might reject it because my MHCs are not the same as yours.
okay.
Your immune system would say, no, that's not right, and it would attack it.
So they try to turn off your immune system.
Right, so then they turn down the immune system with immune drugs that reduce your immunity. But then you're more susceptible to all sorts of things.
But, so they're turning you down so that you can't receive the organ.
Yeah.
Is that like gonna last like? So you're.
Sometimes you have to take them. I had a student who said that her dad had to take them for the rest of his life.
So okay, so I
Yeah.
think if I had somebody's heart and I was taking MHCs, and like I just randomly one day stopped taking them, the heart, like my body would just.
Yeah, could. It might reject it. You might go into organ failure. You can have other things that happen with the immune system that are not so bueno. I like that. Allergies. Allergies are hypersensitivities to certain molecules. We call those molecules allergens. So you have like pollen. Anyone allergic to pollen? Yeah, you're allergic to plant sperm. Yeah, you gotta love it. Plant sperm. Mm-hmm. Yep. Hay fever, for example. That is often treated. Remember, we talked about inflammatory response. Remember what chemical was released in an inflammatory response? Begin with an H. Histamine. Histamine. Good. Yeah. So histamines are released when they shouldn't be released. So your body is producing an inflammatory response, even though there's no infection. So that's the bane of everyone's existence. Sometimes it can be a life-threatening one. In that case, you can use our friend, Mr. Epinephrine, which will very quickly counteract the effects of the allergic response. So some people carry EpiPens around.
Why is it bigger?
Because what the allergy will do is it actually causes the immune system, or causes the body to shut down, like go into shock.
Is it just like overact? Like, is it overstimulating? Like,
It overstimulates it to the point where it just completely shuts down.
So then, but isn't epinephrine like another stimulant?
Yes. So I mean, shutting it down means your heart stops beating.
Oh,
So the epinephrine's like the restarter. Yeah. There's also autoimmune diseases. Insulin-dependent diabetes is one. RA is another one. That's rheumatoid arthritis. I have rheumatoid arthritis. Sad face. If you don't treat it, your knuckles and your joints start looking pretty bad. Your body attacks itself. Yeah, they do that.
But yeah, why does your body do that?
It, for whatever reason, it doesn't recognize yourself as yourself, and it goes after particular tissues. In RA, it's the joints. In diabetes, it's the pancreas. It destroys the insulin-producing cells.
How do you test for that?
Well, for RA, you test reactivity to certain. You test how much. There's these proteins that are present when you are having inflammation that are indicative of RA.
Did you have to get like a needle stuck in your nose?
No, I didn't. Did you have that done? That sounds awful.
Oh no, I got a final tap for mine though.
Oh yeah. Do you have RA?
No, I have too much throat. It's like kind of rare one, but it causes all your blood vessels.
Oh wow. Huh. Just in general, or
Um,
is there conditions that? Is there something that triggers it, or it just kind of happens randomly?
It's the
Mhm.
it's all of your blood cells.
Wow. There's medicine for that? Yeah. Good. Medicine good. Moderate exercise can improve the immune system. Exercise to exhaustion. Riding your bike for 20 hours when you have strep throat is not a good idea. Psychological stress is also not good. Let's see, do I want to? Oh, yeah. Let me just end on this. I want to just touch on zoonotic diseases, or zoonotic. I don't know if it's zoo or zo. It is possible for genes, viral genes, to be passed to humans that can cause disease, and they often come from another species. So this happened in, we think, well, we don't know, but COVID-19 appears to have come from a bat. Swine flu, I think, came from pigs.
Or it was carried by pigs and you could get it.
Yeah. So normally there's a range of hosts that a virus can infect, but occasionally it will mutate enough that it can then infect another host. So COVID-19 probably came from something else. Bats are a very frequent carrier of these viruses, and they oftentimes they'll produce a virus version that can infect us. So when you start looking at bats do it, chickens are another one that you have to really be careful with. Sorry, chickens. We actually have an FDA license? FDA license? And we have to report if there's anything wrong with the chickens. And if there is anything wrong with the chickens, they usually make you cull them, which is to kill them.
Do we produce zoonotic?
Because, well, we have chickens at ETHS, yeah. I was talking about personally, we have chickens at home.
Oh.
But, what was that, Max?
Do we produce zoonotic diseases?
That are passed to other species? That's a good question. I'm sure we do. But we're a little less worried about it than the other way around. They did find some COVID that was being passed to dogs and cats, but not too much. It was pretty rare, fortunately.
Were they affected by the dogs?
Not really. They found it in a few, but I don't think they ever found it in very many.
I think it's super crazy hypothetical, and I feel like this is like.
God, stop it. Sorry, go ahead.
You read the mystery dogs, make them die.
I did see that, yeah. All right, I'm going to stop there.
Wait,